Okay, let's, for more practice here, talk about a surface of revolution. So that is, consider, we'll start off not so bad here, just f of x is equal to x plus 3. That's a very basic graph, right? And we'll look at this for x values between 0 and 7. Now, let's parameterize the surface obtained by rotating the graph about the x-axis. So let's go ahead and draw a little bit of a picture here. So just in the xy plane, xy plane here, we've got we've got starting at x is equal to 3. Starting at y equals 3 because x equals 0 all the way up to x equals 7. We actually have this line segment, which of course ends here at 10. So this is of course our graph of y equals f of x. But we're going to now take this and spin this around the x-axis, and when we do so, we're going to get a picture that looks, well, something like this. Yeah, so this single point here ends up here as well as below, and so we'd have a circle like that, and then this line segment would end up like that, and we keep spinning this around, and we'll have something that looks like this. Yeah. If we so this is what we see from the front of it. What's being obscured in the back, I guess, is a there's this outside largest circle here. Okay, and then there's also, maybe we'll do this lightly, these circles complete this way. Okay, so this is a thing that looks something like a lampshade, just perhaps on its side. Okay, if we were to actually draw this in context, so this object here drawn in context with the x, y, z axes all where they should be, then we should be looking at a picture that, roughly speaking, looks something like this. So there's that. Okay, that's going to get the dotted half of the circle here is because it's going to be hidden from this vantage point in just a moment. But we should have really a thing that looks, well, let's try a little bit of there. It looks something like, roughly speaking, like this. Okay, so sort of like old school, old-timey movie, cheerleaders cone or something, yelling cone, something like that. Okay, let's just point out here that the circles we have circles that are in YZ parallel planes. So if you look at the plane generated by the y and the z axis, every circle that we see here is parallel to that, and the circles are of radius f of x, by the way. So if we want to parameterize this, of course we can do something like this. So x is just equal to u, and since f of x, the value of x, gives us the radius of the circle, it makes sense for the y and z formulas to be f of, well, u now, because u is x, times cosine of v, and then f of u times sine of v. As for a parameter domain, we will here say that u should go between 0 and 7, and v should go between 0 and 2 pi. Now, we can do this, but it might actually just be better for us, just based for the following example, to just say that, you know what, instead of creating a variable called u as a parametric variable, why not just have x is x? So now x is going to be the name of one of the parametric variables, sure. And then y is then going to be f of x times cosine of v, but we're actually going to change the v to just being a theta. We're just going to change the name of the variable just to give it a try. The f of x here, we in our example, scrolling up just a moment, was x plus 3. So let's make that more specific here. So this f of u is just writing things a little more generically. If you happen to rotate the graph of some other function. Okay, so x plus 3 times cosine of theta, and then z would equal, slightly generically, it'd be f of x times sine of theta. And then we can rewrite this as x plus 3 quantity times sine of theta. Again, for the parameter domain, we'll have 0 less than or equal to x is less than or equal to 7, and we'll have 0 less than or equal to v less than or equal to 2 pi. Okay, we're done with this question, but as a follow-up, let's go ahead and find the surface area. Okay, well, we've got, based on the parameterization that we have, let's say right over here, yeah, we've got, we can write as a vector function. Instead of with input variables u and v, we'll have input variables x and theta. If this bothers you, just go with replacing every x that you see here with a u and every theta that you see here with a v instead. Okay, same deal. All right, so then we've got here, just copying from over here, we've got x as the first component, x plus 3 quantity times cosine of theta for the second component, and x plus 3 quantity times sine of theta for the third component. Now, we know based on what we need to do in a moment, we're going to need to compute partial derivatives. Yeah, so let's go ahead and do this. Partial derivative of r with respect to x is going to be the vector function 1 comma cosine theta comma sine theta. And then the partial derivative with respect to the partial derivative of r with respect to theta is going to be the vector function 0 comma negative quantity x plus 3 times sine of theta comma quantity x plus 3 times cosine of theta. Now we also need to take the cross product of these two vectors. So we'll spare some of the details, but if you do r sub x cross r sub theta, you will get the following vector. You'll get x plus 3 comma negative quantity x plus 3 times cosine of theta comma negative quantity x plus 3 times sine of theta. Again, we haven't worked out these details in specific. You're going to have to do that on your own. Now, we'll need the magnitude of r sub x cross r sub theta. So this should be root. Then we need each component squared, so x plus 3 quantity squared plus quantity negative quantity x plus 3 cosine of theta squared plus quantity negative quantity x plus 3 times sine of theta close parentheses squared. And if you work this out, it'll end up being a root x plus 3 quantity squared plus x plus 3 quantity squared. And if you collect like terms and then take care of the x plus 3 inside if you work out some of the details here, you can square root the x plus 3 quantity squared. Eventually, you're going to end up with x plus 3 quantity times a root 2. We won't work through those details right here, right now. Then the area of the surface should be the double integral over d of this r sub x cross r sub theta magnitude d a, yeah? And then, where dA needs to eventually get replaced with du dv, well, that's what it'd normally be here. We are actually going to have them called x and theta. Yeah, so let's have a dx d theta. So integral sign, we'll just leave a little space. We'll have this x plus 3 quantity times root 2. The dA is going to get replaced, as we said, with dx d theta. And then the x integral, as we see over here from the parameter domain, should go from 0 to 7. And the theta should go from 0 to 2 pi. And we will call it quits right there.